Very good. Thank you. I hope you guys had a good break. Let's begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for the time that remains this semester. I pray that you would help us to use it for your glory, Lord. In your name I pray. Amen. Okay, guys, so I think Daniel turned back the homework, which I should probably give to you before I forget. So I wanted to talk to you guys about the how to use the I think that's yours, Nathan. I haven't found a name yet. I use the calculus of residues. Hand that over to Josiah. To calculate certain series. It's an interesting technique. I think there's one of these on the quiz, but I don't think there were any on the homework you just did. So let's see here. So let me just try to walk you through the basic setup. I will gloss over some of the finer points, but it's okay. Most of the details are in the PDF that I have posted by Noah Hughes. Now, okay, so basically, the idea is our goal, you state the goal out front, is to calculate something like the sum from minus infinity to infinity f of n. I mean, that's our goal, is to somehow calculate something like that. And so what we do is we look at, and we're going to assume that this f, and you can tweak this a bit, but this is basically the setup. I assume f is meromorphic. And let's say with finitely many poles. And this is kind of important, non-integer poles. All right. And then, this is the sneaky thing. You pick another meromorphic function, big G, whose poles are at integers. So then, another function. So this is kind of going to be an indirect calculation, much like the residue calculations we've done. Well, some of them have been more or less direct than others, right? Like, surely the integral of like the rational function of sine and cosine, that was pretty indirect. The idea there to make the substitution to turn it into a complex integral around a circle. But on the other hand, I would say that the integrals of rational functions, where we look at like a half circle, the first time you do it, it's kind of weird, right? But after you know one of them, you can kind of figure out how to do the rest of them. This is kind of sneakier. So anyway, another function g, which has singularities only on the integers, but it'll be a little bit more specific than that. In particular, I think I want it to have simple poles. To be more specific, actually, G has simple pole at each z, well, let's say n in the integers. All right. Okay, so then the idea then is if we think about another function, right? If we think about multiplying these two functions together, if you look at g of z times f of z, we call this thing h for the sake of discussion. This is also going to be meromorphic. And what else? Well, where does it have singular points? Two places, right? Where G is singular, and also where F is singular. Now, there's no hope that the singular. I mean, in some sense, these singularities are like decoupled, right? Like the singularities of G are happening at the integers, singularities of F are not happening at the integers. So to calculate the residue of this function H, they're kind of disconnected, right? I mean, you can just calculate one at a time. All right, so then the genius thing then is to look at this particular square, see if memory. So I foresee myself holding my computer over here, n plus 1 minus n plus 1, and then let's see, it goes halfway between those integers up to what's that? Oh, yeah, sorry. So it goes like this. And then, of course, you know, and so forth. Let's see here, and this red curve is going to the halfway point, and if I draw the other axis, here is like in plus 1, and likewise down here minus in minus I times parentheses n plus 1. So let's see here. I'll label one of these corner points. It's really just important to get the idea of this. I mean, it's good to see the details worked out, I suppose, but let's see here. This is n plus 1 over 2 plus I times n plus 1 over 2. That point. All right, and then this red curve we'll take counterclockwise in the usual way. And I think we call it C sub n for following Noah's handout. Are we all on board? So if we apply Cochise's residue theorem, right? What does Cochise's residue theorem say? It says that the integral around Cn of h of z dz, right, is equal to 2 pi I times what? Times the sum of the residues of f, let's say. Let's see here, and that would be g of z, f of z, oops, why am I doing that? G of z, f of z. Let's call these things like z sub j or something, give them a name. Right, so like the z sub, maybe this is z1, z2, whatever. Here's the jth one, right? There's some finite number of those. And then plus the sum over n in the integers, right, of the residue of g of z, f of z, n, at n. Now, of course, I really shouldn't say n in the integers just yet, right? I mean, if I do that, what do I have in mind here? I should put a little preamble if I'm going to say n is in the integers. What do I have in mind when I write that? As n goes to infinity, right? See, as n goes to infinity, you're enclosing the whole real line, right? These singularities, these guys, and then if you get n big enough, eventually you have encapsulated all the singularities of the other function f, right? Make sense? And then the rest of the argument I won't saddle us with the details here, but it's in some detail in Noah's handout that this has to go to 0 for the way this is constructed. So this goes to 0, which is intuitively, I do think I need that I'm assuming that the meromorphic function is meromorphic on the complexes, that there's no singularity at infinity. If there was singularity at infinity, I think this argument would have to be modified. But if there's no singularity at infinity, essentially this is just like some kind of like rational function, right? Where it's going to go to 0, essentially. I mean, roughly speaking, this is the intuition. So anyway, this goes to 0, right? And then we get this wonderful formula, which says that the sum over n equals minus infinity to infinity of the residues of g of z, f of z, comma n is equal to minus the sum, let's say j equals 1 to m, of the residue of g of z, f of z at z sub j, where I'm saying that z1, z2, zm are the singularities of f. So that means we get to calculate a doubly infinite series, right? I mean, from minus infinity to infinity, in terms of just counting a finite number of residues. You're like, okay, but that's great, but this all assumes that there's this magical function g which takes, has singularities only on the integers, and each singularity is a simple pole. With the batteries running low, oh, come on. I thought I had this thing charged not too long ago. There we go. Okay, so come on, where'd you go? So do you guys remember what we take G to be, if you've already worked on this? That's one possibility. Cosecant is the later option. The initial choice is, the answer is not unique, okay? So, cosecant is good. But this is the one I think we do to start with, pi cotangent. And I think pi z is what we do, cotangent pi z. So cotangent basically has division by sine, right? Sine of pi z has zeros, simple zeros, at integers then. And then, of course, cosine is non-zero. It's plus or minus 1 at integer multiples of pi. So cosine pi z is plus or minus 1. And so it's immediately clear that this has, this has simple zeros at the integers. What are those simple zeros, though? What's the residue of g of z, right? Add an integer n. What is that? So we can use pi cosine pi z over sine pi z, like this. Which rule should we use? And we can't always use a rule, by the way, right? You notice that in the homework? Sometimes the rules are no help. Sometimes you just have to calculate. Sometimes it's important just to look at, like, for example, that the problem you had in the homework, the sine z over z cubed. Like, I found myself trying to explicitly calculate the Laurent series earlier this break, and this morning. And so hopefully that wasn't you. But well, let's just leave it at that. But
Use the
Generalized rule 1 and 2. I don't.
You're talking about how you could generalize it?
Oh, I don't know those until the test, though. Because I haven't figured them out. So if it's something I haven't figured out yet, it's natural for me to put it on the test so I can find it out. I mean, you guys will prove it for me whatever it is on the test. I'll be like, just state for me the generalized rule, and then I'll find out what it is. I'm excited about this, Nathan. Okay, so no, this problem, z to the fourth over sine z. So like, you're asked basically this, calculate the residue at 0. I don't think any of the rules are helpful for this one. Maybe the generalized rule. We don't know that yet, though. So the way I thought about it was just this. This has a 0 of order 4. This has a 0 of order 1. So in total, this function has a 0 of order 3. It's very easy to show that this has a 0 of order 3 because you can just write it. Right? And this is analytic at 0. So therefore, the residue of this is 0. But I will freely admit, because I don't do this stuff all the time. If you don't lose it, if you don't use it all the time, you forget it. And I found myself starting to try to actually calculate that Laurent series. Well, I mean, it wouldn't be a Laurent series actually, but trying to calculate the power series. In fact, the Taylor expansion for that at 0 explicitly. Maybe some of you did, right? But that's unnecessary to calculate the residue, isn't it? That's my point. All right, getting back on track here. So how about this one? Basically, we can use what, rule 3? We'll say rule 3. So rule 3 says you take the top, you evaluate it at the singularity, you differentiate the bottom, and you plug in the singularity. Now, it's written in terms of some limits and junk, but that limit just becomes evaluation because there's nothing funny going on here. And you can see that, in fact, that's 1. Right? Okay. Yeah. So there you go. That's the function that has. Well, that's even better, right? Because you can see how does the calculation of the residue of g of z times how's residue of pi cotangent pi z times f of z going to work at an integer? Here's an identity we could have proved here's a proposition we could have proved. See if you believe it. If f of z is analytic at z equals to z naught, then the residue of, well, I need more than that. It's not just that. I need f of z analytic and what else to make it simple? F of z naught is, say, not equal to 0, right? Then the residue of f of z times, say, h of z. Well, I guess I could just do g. I don't want to find little g. Is what? It's just f of z naught times the residue of the g. Why is that? I mean, how did we calculate residue? Residue comes from looking at the coefficient of the reciprocal term in the Laurent expansion for the function, right? So the Laurent expansion for f of z times g of z would be the Laurent expansion for f times the Laurent expansion for g at z naught, right? Of course, the Laurent expansion for f of z is just a Taylor series, right? So its lowest order term is just the constant term, the f of z naught. And then, well, g of z could have a 1 over a reciprocal term, right? But when you multiply those series out, all you get, of course, on the 1 over z term is the product of the constant in the f series with the actual reciprocal term reciprocal order 1 term in the G series. And so it's just this. I mean, there's probably other ways to prove it in terms of our orders of zeros and poles theorems that we had before break, but they fade my mind as we get away from them. Sorry. So anyway, my point to you is this proposition holds here too. So like this residue is really easy to calculate. What is it? This is just f of n times the residue of pi cotangent, you know. Kind of ashamed to write all this because this is just 1. So f of n. In other words, if we use pi cotangent pi z, then if you'll allow me this manga style comment, this is in fact just the sum n equals minus infinity to infinity of f of n, which of course was our goal to calculate that. All right, so let's take this thing out for a spin, see how it works. Let us attempt his first example. He says these examples are from SO. What's SO? Lipschutz in Schiller, Spellman, Spiegel. Sham's outline of complex. Oh, Shams. Funny. He's using Shams to create these notes. It's cool. Where was I? Oh, yes. Thank you. All right. Example, if I don't mark it, it's working better. We're asked to show the sum n equals minus infinity to infinity of 1 over n squared plus a squared is equal to pi over a cos hyperbolic cotangent of pi a, where a is greater than 0. All right, so basically what you see here is that we can apply the theorem I just sketched, but of course didn't. I mean, the picky part about the theorem is mostly what it's demonstrating that, like this, showing this goes to 0. It would take it would take a half hour of our time to really work through that carefully. Anyway, but it's pretty straightforward. So the proof then is here of this problem. We just want to let f of z, f of z is equal to 1 over z squared plus a squared should do it, right? As f of n is what? That's clear. So what do we need to calculate? We need to calculate the sum of the residues. We need to consider g of z, f of z, which is what here? Pi cotangent pi z, right? Divided by z squared plus a squared in this case. There's the singularities at the integers. We already know what happens to those. Those are going to give us the series we're after. And the other term is, well, we need to figure out where are the other singularities here. Singular where? Again, z an element of the integers. We know that's fine. So z equals to n, let's say. And also z what? Yeah, plus or minus a. Nathan, given your interest in computer science, I'm very ashamed that you've given this answer plus or minus a, because the answer is clearly plus or minus ai. You, of all people, should appreciate that.
What does that have to do with computer science?
Wait for it. Okay. If you have to say it, it's ruined. I give up. All right, so.
Oh.
Wow, that was a delay. Sorry for that horrible, horrible joke. Let's see here. So the residue of pi cotangent pi z over z squared plus a squared, and I'm going to be greedy and do it at plus or minus ai, is what? It's pi, cosine, listen to me, cotangent of plus or minus pi ai. And then, so this, I can use rule 3 here because we have, we're assuming that a is greater than 0 and a is not an integer. Okay. I mean, if if a is an integer, this is a different thing. All right. In fact, he covers the case when a is an integer later, actually. Maybe kind of, not exactly. Okay. Anyway, so we just do what? We do 2z. We differentiate this, right? But then plug in. So 2z, but 2z is 2 times plus or minus pi. Plus or minus, not pi. There's no pi here. Plus or minus ai, right? So I'm using rule 3. Are you guys with me? And then we apply the theorem. The sum n equals minus infinity to infinity of 1 over n squared plus a squared is equal to what? Minus pi cotangent of pi ai divided by 2ai plus, I'll put some parentheses here. Why do I have a minus there? Oh, sorry, the minus is part of the theorem. Minus what? Pi cotangent of minus pi ai over minus 2ai. Well, I think I see where the pi and the 2 comes from, right? So we got what? We got, oh, but you know, these minus, the cotangent's an odd function, right? So these minuses cancel, and so we've got minus pi over I cotangent of pi ai, which, by the way, is, and there's an a, I lost my a, let's see here. So we get pi over a hyperbolic cotangent of pi a, and that's using the sinh and cosh as they relate to sine and cosine identities both at once. There it is. Now, I guess often you're like, well, that's great, but I kind of am more interested in series that go from 0 to infinity, right? At least I am. So at this point, because I've only got 10 minutes left, I want to make sure I show you all the nice things I'm going to. And also because I want to test my computer out and see if it works with this projector. Oh, I know. Don't say it. Don't say it. Although this thing has, does this have HDMI? No. This is a more ancient. Oh. Oh. Huh. Yeah. All right. Well, I will forge ahead. There's no VGA output on my computer because it's from like this decade, you know. All right. Yeah, I feel better about not getting, getting my act together and starting using this computer. Like, I've had this computer since the summer, right? I just haven't gotten around to like.
I thought you got it on Black Friday.
No, Black Friday. I have no interest in that. Hmm. They don't do Legos though. They do? You mean I can get like super cheap Legos on Black Friday? Why didn't anybody tell me this? Oh man. Maybe next year. Maybe next year. I'll take my. The Lego company did not go out of business. Nice try. I mean, it's yeah, whatever. Okay, n equals 1 to infinity of 1 over n squared plus a squared is equal to what? So you look at this, right? Now, what's the n equals 0 term? I mean, how did you come up with this? Well, the answer is allegedly 1/2 of what I wrote over there. And then what? Minus the I think it's pi over 2a squared. Is that right? Just, there's no pi there, sorry. And so basically he just uses a rewrite where he says 1 over a squared is equal to f of 0. He, oh yeah, it's very simple. So basically the thing is just to rewrite the sum from n equals minus infinity to infinity of 1 over n squared plus a squared, right? You can write it as the sum n equals minus infinity to 0, let's say to minus 1, 1 over n squared plus a squared, right? Plus 1 over a squared. Why is there a half there? Okay, I guess it's the algebra. Let me just stick with it's fine. I guess it kind of makes sense. Like half of the 0 term goes to the positive side. Half of, I don't know how to understand it. Okay, let's work it out. Sorry, my intuition is failing me here. N equals 1 to infinity. 1 over n squared plus a squared. Right? That's not surprising. I'm just breaking the sum from minus infinity to infinity into 3 pieces. All of this by previous work is equal to pi over a coth pi a. And So then the point is, you just let, like k equals to minus n, then you've got k squared plus a squared is equal to n squared plus a squared, and this thing just becomes the sum k equals 1 to infinity, because, right, k equals to minus 1, k equals to, n equals to minus 1, gives me k equals to 1, n equals to minus infinity, goes to k equals to infinity, because it flips it over, right? And so, usual Calc 2 stuff, right? Just call the thing you want, give it a name, do some name calling. I'll call it George. There we go. Oh, I'm sorry. What am I thinking? Jorge. I miss Jorge. He's a good friend of mine in grad school. Anyway, sum n equals 1 to infinity, 1 over n squared plus a squared. You get 2 of those, right? So you 1/2. And there you go, that's the answer. Yeah. This would have all been much more fun if I could have projected it. Well, we also have this. Oh man, I wish I could project. I wanted to show you the, 1 over the p equals 2 series, summing to pi squared over 6. I think is really neat. Man, I wish I could project that right now. I guess I can't. Ah. But so rather than hurrying through that, I'll just take the last few minutes of class to ask you if you have any questions about the quiz or anything else this week. We have a few minutes. They're what? Oh, well, as you're working on the quiz, is there anything? Nothing?
For problem number 3, you said find the Laurent series expansion, but none of these are actually a nulli. So, like, if it's just a disk, does it essentially just reduce to the Taylor series expansion?
Well, not.
Exterior domain.
Not necessarily. You mean that? Well, I guess the question is the function that I had. What was the function we were looking at?
1 over z squared minus 4.
1 over z squared minus 4. Okay. So let's see here. To kind of give you a big picture of what's going on here. We have singularities at plus or minus 2, right? Now you can talk about the Laurent series expansions about any point, right? But the story of how the different cases possible for the Laurent expansion based on this particular point will vary as we look at different points, right? Like, if I choose one of the singular points, then obviously I can't throw in the singular point into actually the domain of convergence, right? But if so like here, for 2, you see what's going to happen is this is like one of the cases. If I work around 0, right? And that's apparently what I'm doing, right? Here z equals to 0. So that is an annulus, but it's a degenerate annulus. That's one of the cases covered by the Laurent series. So yeah, I think that's fair. The Laurent series is just going to be a Taylor series centered at 0. Fair enough. What was the next case?
It was modulus of z greater than 2.
So there, That was it?
Well, there's
Oh, okay. So the one case. So like, if I can be so bold as to try to communicate by shading on a whiteboard. This is the first part, then part B was like out here.
Yeah.
Yeah. Yeah, there will be a non-trivial Laurent. There'll be reciprocal terms out there. Yeah.
But that's essentially just expanding about infinity, essentially.
I mean,
The thing we did in the, I guess it was chapter.
I mean, you're trying to write f of z 1 over z squared minus 4 equal to a sum, you know, k equals minus infinity to infinity of a sub k times z to the k, because we're centered at 0. So I mean, find the coefficients.
Okay.
Given that the modulus of z is greater than 2. If the it's kind of a quirk of this example that the singularities are symmetrically situated about the origin, right? If we had an asymmetrical setup, right? Like, if you could imagine another problem where you had something like there's a singularity at 2, there's a singularity over here minus 1, right? In that case, the question could have 3 interesting parts. Taylor series in here, genuine Laurent series out to here, and then I think you'd have a different case out here. So, like, this would be Taylor, you know, I think it would be different. There'd be a different one. And then this one, there'd be 3 cases. Because, in the in-between case, between the red and the blue circles, you can't, I mean, obviously you can't shrink, if you're including, say, this point, you can't go closer than 1 because of that singularity, right? But you can't go further than the radius 2 because of that singularity, so you're stuck between those 2. In this example, you get to 2, you're stuck, but then you get past 2, well, there's nothing else to get stuck up on, so it just goes on all to infinity. But the intuitive theorem is just basically the annuli are as big as they can possibly be up to the point they bump up into the next singularity for your function, assuming that some kind of global formula is given, of course. Now, what was the other case? You said I was centered at
It was z minus 1 plus than
z minus.
z minus 1.
So it's centered at, so z minus 1 less than what?
C.
Oh, c. What is c given to be?
It says find the largest possible value.
Ah, well, I can't say too much, but if you think about this, that'll work. This would work, right? You can't have a singularity within the domain, within the domain of convergence for the Laurent series expansion, right? So I really can't say much more without answering that, what C is. But, and I actually say to find it too? To find the Laurent series, or you just say find the C?
This is calculate the first few terms.
First few terms. Oh, okay. Oh man, I'm getting to be too nice. To actually find it would be kind of a bear, but yeah. What's C?
1.
Yeah. You can thank Nathan for that. Okay, because when you get to C equals to 1, you hit to the singularity at 2. All right. Anyway, I will shut up, and I'll see you guys Wednesday. We'll talk about the quiz and whatever questions you have.